Welcome back to another video. We got lab for magnetic fields of a bar magnet. Let's get started. What is this lab all about? So the main purpose of this lab is to measure the distance-dependent magnetic field of a small bar magnet and then to compare observed versus predicted distances of the on-axis and off-axis magnetic fields that will be derived from the Biot-Savart law. For the predicted distances, as always, we're going to be using GlowScript as our computational model, and here is just a quick preview of the results. So time for the fundamental physics principles. And for the first time, we don't have Newton's second law. So what do we have? First up is the Biot-Savart law, named after two French dudes who discovered the relationship between the magnetic field at a point and a tiny circuit element, expressed by this equation. Next up, we got the magnetic fields of a dipole. Now, a magnetic dipole is just a closed circulation of an electric current system. What does this mean? Basically, inside the magnet, we have a bunch of electrons circulating around atomic nuclei while spinning on their axes. This creates a dipole with a magnetic field strength given by this equation. Finally, the distance-dependent formula, which states that the magnitude of the magnetic field due to the bar magnet falls with distance. And with this formula, we can also linearize the relationship as we'll see in our graph soon. Let's get started with the experimentation. First, we need to orient our phone to make its magnetometer orthogonal to Earth's magnetic field. Um, Lastly, next we'll need to find the location of the magnetometer chip on the phone by following these diagrams. And lastly, we measure the distance between the magnetometer and the bar magnet for the on and off axis scenarios. For this lab, our system will be the bar magnet and the surroundings will be everything else. So here is the data for the on-axis scenario. To the left, we have the distances, measurements for different magnetic field strengths, and on the right, we have a linearized plot of the averages. Based on our distance dependency formula and the equation of the best fit line, we can determine the variables of n and k. Now that we know n and k, we can solve for the magnetic dipole moment u, which is found to be 4.613 amp-meter squared. Our next scenario is the off-axis magnetic field. This procedure is similar to what we did for the on-axis case, except now we move the magnetometer perpendicular to the direction of the axis. The result for x, y, and z components of the magnetic fields at a perpendicular distance of 0.196 meters are given in the table. And now that we got the observed data out of the way, we can move on to the computational model. The first step is to create a function for the magnetic field and set up our initial conditions, particularly the magnetic dipole moment we found in the previous steps. Here I coded the visual aspect of the model. To do this, I specify the magnetic and the magnitude and direction of the two on-axis arrows, four perpendicular off-axis arrows, and one arrow 45 degrees from the axis. The predicted magnetic field is highlighted in blue, which is relatively similar to our observed model, though there are some discrepancies. In this lab, we had to make a few assumptions and had a room for potential error. The main assumption was that the bar magnet acted as a magnetic dipole, and the main error was that other electronic and magnetic objects in the room skewed the magnetometer data. So here's a little quick quiz about the observations we made in this lab. The true statements are 1 and 4, which accurately describes the distance dependency formula and what we saw in this lab. For a deeper dive and discussion of the data, we have two what-if questions. First off, what if we hadn't compensated for magnetic north and instead placed our meter stick at an intermediate angle relative to Earth's magnetic field? Well, Earth's magnetic field wouldn't interfere with the bar magnet's magnetic field, and this would skew the results. It would interfere. Next up, what if we connected two identical magnets end to end and repeated all these experiments? Well, the magnetic field magnitude would roughly double, but the direction would stay the same. And as per usual, thank you so much for your attention, and I hope you have a great day.